Start off with an equation. How do you begin? Huh?
Plug in the series and the derivative.
Okay, so what is it going to look like?
1 sigma and it's 0 and 2 infinity. I mean, you could put 2, but it doesn't matter.
Oh, this is
N minus 1.
N minus 1.
It's a and x to the n minus 2. And the second one is plus the same thing, but instead of n minus 2, it's just n. And then minus 4. That's n, a, n, x, n. And plus 6. 6 to 0 to a n x to the n.
What do we do?
And then you just fix the first term.
Okay.
It has to be, we set n is equal to n plus 2.
We're going to fix the powers.
Yeah.
So that's going to be go from 0 to infinity. N plus 1 is this guy. N plus 2. N plus 2. That's the n. This one,
You don't have to fix any of the others.
you don't have to fix anything, and in fact, we can start him from 0, right? And it won't actually make a difference. So this will be n minus 1, n minus n. This guy, well, we don't have to do anything, and also we can start from 0 without any consequence. And this guy's already started at 0. So we can get this to have the same index and the same powers without too much trouble, which means ultimately we're going to put one big series and
Wait, quick question. Why wouldn't the others change, but just like the first one?
why did what?
Why is it just the first one that changes, but not the others?
What do you mean the first one?
Like, on the power?
These all had power ends already. There was nothing wrong with
Okay.
them. Or we assume our solution looks like a and x to the n, so I want everyone to look like an x to the n. So I shifted the powers. Simultaneously, I could shift the index without too much trouble. I could just start it at 0 instead of wherever it started, and it was fine.
You can simplify it
And
if you want.
yeah, so now what we're going to do is we need the inside equal to 0. And what are we going to solve for?
A n plus 2.
A n plus 2. We solve for the largest index. It's going to be a bunch of stuff divided by n plus 1, n plus 2. And on top, well, there's a common a n. And what is that?
N squared minus n minus n squared minus 5n.
That's n squared minus 5n
Plus 6.
plus 6. Does that factor?
Yes. Minus 3.
Negative 3, negative
minus 2.
Minus 3 and minus 2?
Yeah.
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 Okay. Kind of disappointed. I was hoping something would cancel. But nothing canceled.
I'll touch it like that.
So this isn't the answer. But this, what did you say?
It sounded like you were doubting us. I was like, damn, that's the only good thing about it. Come on, really?
Yeah, like, do you guys really know how to solve this? We can double check, yeah.
How come on the third term the power of x doesn't change when you change the index from 1 to 0?
Oh, because I didn't need to change the index. I didn't need to actually do a shift in order to change anything. Or I didn't need to evaluate terms. What I actually did was, this starts at n equals 2, right? But notice that if I started from 0, what would happen? 0 would be plugged into here, so I'm adding 0. Then if I start at 1, make this 0, so I'm adding 0. So essentially, these two series, they're exactly the same.
Wait,
Right.
is that the same thing on the third one?
Pretty much the same thing on the third one. Starting at 1, I can start at 0 without any consequences. If I plug in 0, it's like adding 0.
Okay, so you're not
So it's
just
like
doing a shift in that sense, you're just rewriting it that way.
Yeah, I just want everyone to start at the same point. And I realize I can just literally do that and not really affect anything, because I'm essentially adding 0 1 or 2 times.
And it doesn't matter if you start from like -1, because it's still 0, right? If the index is like a negative number.
Yeah, technically. So, but all of these would be 0s, and that would be an A1. Once we talk about that, we'll talk about that a little bit more later. So, finally, now what do we do?
I'm sorry, but how did you get the first, the breakdown of the 1 plus x squared term over there? It's actually the y double
Distribute.
prime?
It's y double prime plus x squared times y double prime.
Where's
So the first one is y double prime.
Uh-huh.
This one is x squared times y double prime.
You just visualize.
Oh, okay.
This is 1y double prime plus x squared times y double prime.
Mhm.
This is y double prime. Multiply that by x squared, it just bumps up the power by 2. So we get this.
Okay, I
So
see
it's
it.
y double prime plus x squared.
I see it now, thank you.
Yes.
You said for y prime, if we plug in 0, we get 0. Plug in 1, we get 1.
We get 0.
Yeah, we get 0.
Yeah.
You can do the same thing with y double prime, that's sigma, which still added to the one above green.
This?
Yeah. That one.
I can't. If I plug in 0 for n, I don't get 0.
Well, if you plug in this first one, yes.
I won't get 0. I would get 1 times 2 times a sub 2. X to the 0. I wouldn't get 0. So now we just use that guy to compute a few terms. Remember A0 and A1 are just whatever. Technically these guys would be our initial conditions if we were given any, but we were not given any. So I'm going to ignore them. A2, and I start by using that guy. A2 would mean I plug in n equals 0. And I would have what?
6
Six.
a.m.
Divided by
3?
3, yeah.
I know, it's 2.
Yeah.
Oh,
So you already-
I shouldn't have believed.
There's your answer, Owen.
Oh.
Like, Jesus doesn't trust us. You have to double check. You have to double check. They just multiplied 1 and 2 and got 3. So I have to double check. Come on. To get A3, you plug in n equals 1. You would have here -1 times -2 to A1 over 2 times 3. A4. To get A4, I plug in n equals 3.
And equal 2.
And equals 2. And
That's 0.
Yeah.
Yeah, you get 0.
A5
is also 0.
and A5.
0.
That is going to be when you plug in n equals 3. That is going to be 0. A6. Getting mixed up with the color. A6. That's when I plug in n equals 4. That means I'm going to get an A4, something blah blah blah, A4 or blah blah blah. That's 0.
Wait, how'd you figure that one out?
Come again?
How'd you get 0 for A4? I mean, 0 for A6.
Because A6 depends on A4, right?
Oh.
Because AN plus 2 depends on AN.
Oh.
So A7 is also 0.
A7, well, that's going to be blah blah blah, A to the 5th, right?
Yeah.
So that's going to give you 0.
So it's just gonna be
Oh,
0?
wow. Yeah, this is just gonna.
For every single.
So there's actually a finite power series, that's all. Yes,
Could you go with that?
you're okay up here?
Yes, well,
Okay.
up to 5.
Okay, yeah, to get A4, I plug in n equals 2, so that way I get A4 on this side, but n equals 2 is going to make that 0, right? Because I plug in n equals 2, that's just 0. Similarly, to get A5, I need to plug in n equals 3,
That's what I'm saying, I'm fine up to 8.
but n equals 3 is going to make that 0. Okay.
A6 and,
Now to get A6, I need to plug in n equals 4, because n plus 2, for that to be 6, n would have to be 4, but notice that over here I would get A sub 4. I would get some number times A4, but A4 is 0, so that whole thing is just going to be 0, because the A4 is 0.
just like A5.
And then to get n equals 7, I plug in, to get A7, I plug in n equals 5, that's going to give me 0 in here, and I get, and pretty much you'll see that everyone else is going to be dependent on the guy 2 steps back. So pretty much a n equals 0 for all n greater than or equal to 4. In other words, what does that mean? There's a finite power series solves this. So this is actually solved by just a regular old finite length polynomial. In fact, so now I can write down the answer. It's y equals a0 plus a1x plus a2x squared plus a3x cubed plus a bunch of zeros.
How did you get that?
Quick question.
Yes.
It then ask how many, for a significant number of
Yeah.
powers,
Yeah, because I only care about 4 anyway. You could find more, but it wouldn't really. So it turns out that y equals a0 plus a1x plus 3a0 x squared plus a1 over 3 x cubed is our solution here. So we have a linear, if you want to write it as 2 solutions, this is just a0 times 1 plus 3x squared. That's going to be your y1. And plus a1 times x plus x cubed over 3. That's going to be your y2.
Will you ask us for in that format on an exam? Like with the y1 and the y2 separated?
Yeah, usually. I either tell, not only would I ask the question, but I'll describe to you exactly how I want the answer. So I might say something like, just give me the first 4 non-zero terms, something like that. Or make sure you separate it so that I see the 2 linearly independent solutions. So I'll tell you that.
If there was, for instance, a y3, how would you prove that y1, y2, and y3 are linearly independent?
There's not going to be a y3, it's a second order.
What if there were?
They're tangent.
No, I mean for a different example. For instance, if that was y third prime. and
Y
then-
to the triple prime?
Yeah, and there was a y3.
Yeah.
So how would we prove that all y1, y2, and y3 are linearly independent?
Oh, the 3 by 3 runs. Yeah, you do the 3 by 3. What we did last time, you just do the 3 by 3 version.
Which you would plus.
Yeah. Which,
Yeah, but that's-
yeah, like a Laplacian expansion, you'd have to find the 3 by 3 determinant.
I don't know.
Yeah, but I wouldn't actually ask you that. For power series, we're not going higher than second order.
Thanks.
In the book, they anticipate you knowing the general form of arctan and hyperbolic cosine, hyperbolic sine. What specifically we need to know? E to the x 1 over
E to the x, 1 over 1 minus x, sine, cosine.
just those
That's
4?
it?
Yeah, that's really. Hyperbolic sine and cosine is just like sine and cosine, except there's no alternating sign. So just remove the minus 1 to the end. From the sine, that's your hyperbolic sine. Remove the minus 1 to the end from the cosine, that's your hyperbolic cosine. For arctangent, just remember that we can integrate power series. So I remember that the integral of 1 over 1 plus x squared gives me arctangent. So I wouldn't remember arctangent, actually. I would just think of this as 1 over 1 minus x squared. that I can write as a series minus x squared to the n, and then I integrate that, and that's my arctangent power series. I wouldn't even remember that. You can actually just derive that pretty quickly. So I don't know if they expect you to know it or they expect you to be able to derive it very quickly, but I'd also expect you to be able to derive that very quickly. Yeah, but once you know those that I mentioned, you should be able to build any other one reasonably well. Because those power series are absolutely convergent on their radius of convergence. And so we are allowed to integrate and differentiate. Okay, so that was just a trick. Now, well, that was just another example just to remind you of how this game is played. Last time though, we noticed something.
This game is hard.
So it's one that you have to get used to. Last time we noticed something though. We did a bunch of things where we had to evaluate a bunch of terms, right? And then we realized at the end of the day that the thing that the recurrence relation would have given us already coincided with the terms that we evaluated, right? Which kind of makes you think, was it necessary to evaluate those terms in the first place? Right? I mean, it had to work out, right? Like that recurrence, that we assume that a power series describes the entire thing. So the coefficients that make the series work would have to also make these extra terms work. So now the question is, do we actually need to worry about the index as much as we did, right? We got those terms because we wanted to get the indexes to be the same. So there's another way, ladies and gentlemen. So it's a variation. By the way, solving something using power series is called the Frobenius method because this dude named Frobenius is the guy who figured out the theory about how all these things work. So you can do a variation on the Frobenius method. So you might hear that referred to as the Frobenius method. Whenever you hear someone call it the Frobenius method, they're talking about using ODE, using power series to solve ODEs. So here's the thing, instead of y equals some power series that looks like a n x minus x naught n, assume y equals a Laurent series, going from minus infinity to infinity of a n x minus x naught n, with the stipulation that a n is equal to 0 for n less than 0. So pretend that the series goes in both directions an infinite amount, but we just pretend all coefficients below a0, they're automatically 0, right? So, of course, finding the solution of this form is pretty much exactly the same as finding the solution of that form. What is the benefits of making this assumption? Well, I don't have to worry about shifting the index. If I shift back 2, okay, I'm 2 more deep into negative infinity. No difference whatsoever. I do not have to worry about evaluating terms and getting people to start at the same point. They will always actually start at the same point. And so this allows us to combine series without fixing indices. Will always be the same. Now, we kind of saw that last time. I'm just going to actually write out a solution using this assumption as opposed to the other one. And just to make sure you're convinced that it does work, I'm just going to redo the answer that we actually noticed this for in the first place.
Yeah, didn't we, anytime we needed to change indices after we'd already changed the powers, didn't we notice that any smaller number you would plug in and then just get 0 terms? So we just always change that number for the index?
Yeah, so I'm saying we don't actually need to do that. So let's redo fall 2011. problem with this new assumption. So that guy was this one. So you might like this. Now I'll talk about the pros and cons of doing something like this, especially in the next thing, the next kind of series solution that we're going to want to do. There are pros and cons to doing this, and I will talk about them. So find power series solution centered at x equals 0. So what I'm going to do is I'm going to assume that my...
Oh, we did this last time, right?
Come again? We did this last time, yes. So I'm going to assume that my y is equal to, from minus infinity to infinity, of a and x to n, where a n equals 0 for n less than 0. So the a sub minus 1 term is 0, the a sub minus 2 term is 0, etc. So what would that look like? Well, I would have the series from minus infinity to infinity. At some point, I'm just not even going to bother writing them because it's not even going to matter. Of 3n, n minus 1, a n x to the n minus 2, minus the series of n minus 1, a n x to the n minus 1, plus the series of n, a n, x to the n plus 1, plus the series of a n, x to the n, plus the series of a n, x to the n plus 1 equals 0. Right? Where all these guys are from minus infinity to infinity. It's called our own series. They're all the rage in complex analysis, which is actually a good course for engineers to take. So, engineers and physicists, a background in complex analysis will actually take you far. Now what's going to happen? Well, I'm going to shift the powers. Right? Get all powers to the n. What would that mean? Change all n's to n plus 2's. What's going to happen to here? Nothing. It's going to be the same thing. So, in other words, I can just start writing out one big series from minus infinity to infinity, because the indexes aren't going to be changed by me shifting the powers. So ultimately, everything here, I can just start just shifting the powers and then write them inside in one step. So it'll save you a couple minutes because you save yourself a couple lines of work here. So this one's for Chris. He asked me for shortcuts, so here's a shortcut.
Thanks, Jhevon.
Deliver. Okay, so here you have 3, n plus 1, n plus 2, a, n plus 2. Here I would have minus n, n plus 1. Here I would have, I'll shift all n's to n minus 1s plus n minus 1. Don't forget the a n plus n minus 1, a n minus 1.
A n plus 1?
I shifted to n plus 1, n plus 1,
That was
a n plus 1.
Yeah.
This guy, I shifted to minus 1, so I get that. And this guy doesn't need to be shifted, that's just a n. And this guy needs to be shifted by 1, so that's a n minus 1. Now, once I do these shifts, the indexes aren't going to change, they're all going to be still the same. So I can just jump straight into the recurrence relationship. So I'm going to solve for my a n plus 2. It's going to be a bunch of stuff divided by 3 times n plus 1 times n plus 2. And what are we going to have? n plus 1, a n plus 1. That's for this part. Plus 1 minus n, a n minus 1. But this guy actually will kill that.
It should be n minus 1, not 1 minus n.
No, I was bringing it over the equal sign. So.
Oh, yeah, yeah.
But let's just cancel those first, so I would have minus n, a n minus 1, and then minus a n, right? So that is my recurrence relation, and I'm just going to generate everyone from this, and I believe we only needed the first 4 terms. So your a0 is going to be your y of 0, your a1 is going to be your y prime of 0. Did they tell us what those were?
No.
Yes, y of 0 was minus 6. And y prime of 0 was 2. And so now, a2 is going to be equal to, when I go to that formula and I plug in n equals 0. Plugging in n equals 0, 0, 0, I get minus a0 over, what is that, 6?
Yes.
Now, if I plug in n equals, for a3, this will be n equals 1. Plug in n equals 1, I would get 2a2 minus a0 minus a1 over n equals 1. So that's 3 times 3, that's 9 times 2, that's 18. So now this guy, a0 is minus 6, so if I plug in minus 6 here, I just get 1. And over here, that means for a2 I can plug in 1. For a0 I can plug in minus 6. For a1 I can plug in 2 over 18. Those cancel, get a third. And I stop there because the problem asks for the first 4 terms. This means my y is equal to a0 plus a1 x plus a2 x squared plus a3 x cubed to 4 terms. And
That's always the standard form of y, right?
huh?
That's always the standard form of y, or is it ever going to change?
The only way it can change is if it's what your x is. If your x is centered at something other than 0, it's going to be x minus x naught.
Oh, yeah.
But yeah, we always make it look like an infinite polynomial
But that, yeah.
with x minus x naught. Here our x naught was 0. So a1 was 2, a2 is 1, a3 is a 3. So that's our y correct to for decimal places.
I have a question. When we do the first line, the y is equal to a0, a1x, we do that because we assume a polynomial can approximate any function, right? An infinite polynomial.
We're assuming that the power series can approximate our solution, yes.
Any solution.
Yeah, well, the solution to that. Power series can approximate any solution. For a function to be able to be approximated by a power series, 1 has to be infinitely differentiable. 2, the derivatives have to not be crazy, meaning they don't grow faster than factorials, because then the ratio test fails and we don't have convergence.
But we always assume it's absolutely convergent.
Huh?
Yeah,
we want it to be absolutely convergent, because otherwise the calculus isn't going to work. Because I'm like, I don't know what function I'm differentiating. Could be anything by you rearranging the terms. So to force absolute convergence, we need that the derivatives don't outmatch the n factorial in the Taylor series formula, because then things can go really bad. Yeah. And there are other functions with some peculiarities where their Taylor series actually doesn't match them very well, but for us, these will match them very well enough. Frobenius kind of worked out all the kinks here, just he hoped. Maybe a power series will solve this, and he did it, proved it after the fact that it works out. Yeah, so that's that. So That was a lot quicker than last time, right? See, this is what I'm talking about. Once you kind of get used to it, you've seen a couple, you're like, it's not so bad. It still takes a while, but it's kind of like curve sketching in Calc 1. First they did that, holy crap, that took forever. It took like half an hour, 40 minutes for one of them. But by the time you got to test 1, you should be taking like 10 minutes. Yeah, so the same thing here. So you do have the option of not worrying about the indexes. Just make that assumption in the first place, and you never have to worry about shifting anything. There are benefits to shifting, but it's kind of like it'll be an extra check for your work, which I will talk about pretty soon. Let's actually talk about.
Would you recommend then that we mostly use this method? Or? Okay.
I'm not going to fault you for doing this. So just make sure you do everything correctly. You're fine. Now, we want to segue into solving a different kind of differential equation at certain problematic points, but we're going to have to take a detour before we look at the method to solving that. So, remember, I told you what singular points were, I believe.
Yeah.
Yes, right? So, we are going to want to solve differential equations at power series where we're close to or centered at a singular point, which provides its own challenges. So recall for p of x, y prime plus p of x, y prime plus r of x, y equals 0. X naught is a singular point. Right? A singularity happens here. If p of x naught equals 0. Because our theory is kind of built up on the fact that we can kind of solve for the highest derivative, that's how we got to put it in that matrix and use linear algebra to help us figure out the theory. So we'd often want to put a differential equation in standard form. That's going to require us dividing through by the p of x. Now, wherever the p of x hits 0 is obviously going to be a problem in that situation. So even if the functions were continuous in the beginning, me dividing through by p of x and putting it in standard form to be able to use the machinery that we've developed is going to be a problem. We'd like to be able to solve ODEs close to their singular points. So we can actually find a solution there, but sometimes a singular point is really damn interesting, and I want to be able to solve a solution close to there. I'm going to want to approach the singular point and see if things can work out. To help us, we look at, there's something called the Cauchy-Euler equation. Cauchy, yes, very famous mathematician. A lot of the times they actually leave his name out of it. But the Cauchy-Euler equation is thought of in more general terms. Usually when someone says an Euler equation, they mean a second order Cauchy-Euler equation. So it's kind of like when you have Gaussian elimination and Gauss-Jordan elimination. Right, the more mathematicians' names you have on a thing, the more badass it is, you know. So yeah, if we're only thinking of second order, we just need Euler. We don't need the Cauchy really. So a Cauchy-Euler equation is something that looks like this: x to the n, y to the n derivative plus x to the n minus 1, y to the n minus 1 derivative plus x, y plus. Technically these can have constants in front of them. a n minus 1, a1, a0, 0. We're not going to go higher than the second order version of this because engineers rarely ever need anything higher than the second order differential equation.
Quick question.
Yes?
Was Cauchy also a physicist? Of any kind?
Well, I mean, a lot of the mathematicians dabble in both math and physics. Gauss, all those guys. Like back then, the subject was in its infancy. You could know all the math in the world. You could be like one guy knowing all the math in the world. So right, you know how to apply it to a bunch of things. So a lot of these guys, they made contributions in chemistry, in physics, in biology, all over the place. They were like science men, power men. Okay, because back then the math was everything, and they knew everything quite literally. That can't happen today though. Like you have hundreds of PhDs every year with new research. No one can keep up with it all. It's just, yeah. Those days are gone. That's why you don't hear about big names like that anymore. Okay, so we care about the second order. So for us, I'm going to define something called an Euler differential equation. And for us, it is going to be an equation that looks like this. Alpha, it's just a constant, we just use Greek letters. X squared, y prime, plus beta, x, y prime, plus gamma, y equals 0. Let's consider this equation. So we're going to play our old game. We're going to guess a solution that might work. With the x squares there, the e to the rt seems like it won't really do the job. There's a way to force it to work, but what you realize is by forcing that to work, it's equivalent to what I'm about to do, so we're just going to do it this way because existence in unison. So we're going to do the easier way, because why not? The idea is, again, you want to be able to combine terms after taking derivatives so that they cancel each other out, which means you want the derivative to be similar to each other. Now, because the coefficients are polynomials, it kind of makes sense for you to pretend that the solution might look like a polynomial. That way, this is a polynomial, that's a polynomial, that's a polynomial. We have a bunch of polynomials canceling each other out to get 0. So we're going to assume our y looks like, rather than e to the x to the r. Look like a power of x. It's going to be some power of x that is going to somehow create like terms, and then you can cancel them out.
Oh, it's like variation of parameters, kind of?
Not quite. It's more like just guessing a solution that we think will fit the pattern. Variation of parameters, no, that variation of parameters comes in when you're looking for a particular solution. Here we just want to find the general.
Oh no, the other thing, but like it's e to the rt. Well, kind of.
It's the same idea behind assume y equals e to the rt.
Yeah.
So, if we made this assumption though, what would our characteristic equation look like? This means that our y prime will look like r x to the r minus 1. It will also mean our y double prime looks like r times r minus 1 x to the r minus 2. And of course, they're going to plug those guys into this equation. Call this equation 1. Plug into 1, and we would get alpha x squared times r minus 1, x to the r minus 2, plus beta x times r x to the r minus 1, plus gamma times x to the r equals 0. What you're going to realize here is that you have alpha x squared. Well, you can combine these x's. R times r minus 1, x to the r, plus beta r x to the r, plus gamma x to the r, which you could factor this out. Now, we're going to make a very simplistic assumption. Let's assume our solution is more interesting than 0 itself. So, assume x is non-zero, and I can divide by it. This means I get alpha r minus 1, plus beta r, plus gamma equals 0. This is another quadratic equation. I can solve that to find the r that's going to work. This is not called a characteristic equation though, even though it functions as the same idea, it functions in the same way. It's called an indicial equation. Because you use it to find the indices of the x that's going to work. So we call it an indicial equation.
Do we also assume that r cannot be 0?
No, you make no assumptions on r. R could be 0.
If it was 0, then it'd be y is equal to 0 raised to the power of 0, and that's an determinant.
Huh?
If r is 0, and...
Yeah, but my x isn't 0. So-
Okay.
So we call that an initial equation, same thing as a characteristic equation, we just call it that. Let me write it this way, it performs the same function as our characteristic equation. Okay, now, this is going to be a quadratic. So again, there are 3 possibilities. We can have 2 distinct roots, we can have 1 repeated root, or we can have complex roots. And just like with the e to the RT situation, these break down into 3 scenarios that we know exactly how they're going to look. So we have an equation like this, we pretend that's a solution, turns out we get that initial equation, we can use that to solve for r, and that will give us the solution to this guy. So now we have 3 cases. 1, we get R1 not equal to R2 distinct roots. Now in this case, your solution is going to look like C1x to the R1 plus C2x to the R2, right, by the superposition principle. If I know one is a solution, any linear combination of any 2 solutions is a solution. And we know from the existence and uniqueness there that the solution is going to come in 2 parts, and so the solution is going to look like that. What if you have a repeated root? So case 2, you have r, a repeated root. So here's what this solution looks like. Y equals C1 x to the r plus C2 x to the r. Now, if you multiply by an x, which you might be thinking, that's going to change that to an x to the r plus 1. That actually doesn't work. What you actually do is reduction of order. You're going to pretend the solution looks like some function times that solution, and it turns out you will end up with an ln x. Now, that might seem strange to you. To give you some comfort, even though it's not really an argument, the idea here that you can see why that kind of makes sense is that if I look at x to the r, and I think of it as an exponential, that would be e to the ln of x to the r, assuming my r is greater than 0. And this, I can move this down, so it's e to the r ln x. So it's like this guy, the ln x functions as the t from before. So when you have e to the rt, you multiply by a t, you have e to the r ln x, multiply by an ln x. It kind of, the pattern works out the same. It is something you should prove though, but that's how it's going to be. A repeated root in the Euler equation case multiplies by a lot.
So those 2 solutions would still be linearly independent, or linearly dependent, right?
Linearly independent. X to the r and that guy, they're independent.
No, I meant the first ones, which is why we did this, right?
Which
So
first
we couldn't just multiply by x because it would still be linearly dependent, right?
No, because those guys, they could not be linearly independent in general unless you contain the origin. Multiplying by x, why we didn't like that is because it would actually contradict what we assume the solution looks like.
Okay.
Because it would look like an x to the r plus 1 instead of x to the r,
Okay.
right? So, the third case, again, thinking of it as the exponential is going to help us figure out the third case. I didn't write cases. So 3, your r is equal to a plus or minus in in this case, your solution is going to look like C1, x to the a, cosine of b ln x, plus C2, x to the a, sine of b ln x.
Quick question.
Yes?
So the cosine sine, say what it, oh,
Oh,
And I think, well, why is that? Why would it look like that? Well, in the same way, if I have x to the a plus ib, then what I can do, this is just x to the a times x to the ib. This is, I can write this as e to the ln of x to the ib, which of course, you can bring that down. This is x to the a, e to the I times b ln x, right? And then use Euler's formula. That is cosine of b ln x plus I sine of b ln x. Then you throw in the arbitrary constants and you get that back. So, these are the three cases for the Euler equation, the second order Euler equation. Let's do some examples. And then, hopefully time permitting, I can show you. How are you going to use this to talk about singular forms? Love to see where you go with this.
If you were
You were probably saying that to Euler, what the hell are you doing with this? Just watch.
If we were confronted with like a random ODE, could we always use power series to solve it?
Yeah.
So any random ODE, so solve it in like a reasonable amount of time.
In fact, we did one. Remember, we did y double prime plus y. We knew to solve anyway. That just gave us an r squared plus 1, and we actually got the sine and cosine, remember? By doing the power series, we actually figured it out. So the power series will work to what we expect it to work to whenever it works. One thing I have to mention here, notice that we have ln's involved, so now you have to worry about x being negative. So for the ln, we further assume x is positive. But it doesn't mean that we can't solve it in the negative case. If our x can be negative, we simply put absolute value x in place of x above. And it kind of works out because, as you would have learned in Calc 1, the derivative of ln x and the derivative of ln of absolute value x, they actually work out to be the same. So the calculus actually deals with them very similarly. These are both 1 over x, so it kind of works out. Okay, examples. So these guys are going to feel just like the e to the rt guys, but they just have a slightly different characteristic equation, which we call the initial equation. And so finally, the general solution. These two, assuming x is not equal to 0. This one, assuming x is larger than 0.
get to the part where like we have to find the homogeneous part and the particular part, and then we have to add them up to get the whole y, or no? Or these
I
equations-
probably wouldn't ask that.
Oh,
But if I did, it would be, nothing would change between what we did now and before. If you're doing undetermined coefficients, you again pretend it looks like this and not like that, or the variation of parameters are actually. So, as you might recall, when we were proving the variation of parameters method, I didn't assume that the coefficients had to look a certain way. It's going to be just the Wronskian of this thing, and divide through by the Wronskians and all that stuff. Okay, let's do 8. Okay, so just like last time, we're going to jump right into the characteristic equation. So our initial equation, what is it going to look like?
X, y is equal to x to the r.
Yeah, the initial, we skip all that, we jump straight to the nitty-gritty.
Alpha is 1.
Yeah, so alpha is 1, your beta is -4, your gamma is +4. Then it's 1, r minus 1, minus 4r plus 4. Right? It's alpha r minus 1 plus beta r plus gamma. Right? So that's what the equation is going to look like. Right, so instead of an r squared, we have an r times an r minus 1. So this gives us r squared minus 5r plus 4. What is that equal to?
R minus 4 minus 1.
So that gives us two solutions, r equals 4 or r equals 1. Which means our solution is going to look like C1 x to the 4 plus C2 x to the 1. And technically here, since our x is non-zero, potentially it's negative, you want to put the absolute values. So that'd be what your solution is. The x to the 4 is not going to care, but the x is going to care if it is positive or negative.
wouldn't it be positive regardless because it's on an even power?
Again, this one is this one,
Oh,
yes,
oh,
but
yeah,
not
yeah,
this
yeah,
one.
yeah, yeah.
So absolute values, since it may be x is less than 0. So negatives are possible with the x not 0. B. Initial equation.
R squared minus 4r
R minus 1
minus
4 equals 0. R squared minus 4r plus 4. So you get
our formula.
it's r minus 2 all squared. So r equals 2. We have a repeated root. This means our solution looks like C1
X to the 2.
x squared.
Absolute.
Yeah.
Plus C.
Even though that's not going to make a difference, C2
X to the 2 is natural log of x.
natural log of x. That's our solution. So the third one, we're assuming x is positive, so I don't have to worry about those absolute values.
Could you explain why it has to be absolute values for in the first example, like where there's no ln? And for a. It might be x plus less than 0.
Well, because of, in order to coincide with the general theory. So to figure out these formulas, remember we replace x to the r with, we thought of it as e to the ln of x to the r. So in order for us to even make that manipulation, to come up with these cases in the first place, we needed to make sure that an ln was allowed. So even though technically it doesn't seem like it would make a difference there, just to make all the cases flesh out using the exponential, we needed C.
Professor,
Yeah.
can you change C to a non-homogeneous and show us like how to still do it the other way?
Yeah, like I was saying, literally nothing would change. Like if I put, so if here there was something like, okay, let's say on that side I put X, then you would assume the solution looked like AX plus B. You multiply through line X to make it not overlap with that. You plug in here, solve for the A.
Oh, we just use undetermined coefficient?
Huh?
We just use undetermined coefficient?
Undetermined coefficients, variation parameters if you're into it, either one. But yeah, nothing changes about finding the particular solution. So you just make a guess or use variation parameters. Okay, conditional equation.
4r squared minus 4.
R squared minus 4r plus 8r plus 4r plus 17. How do you solve that? Quadratic formula is minus b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Now, 16 is a common term here, so I can factor that out. I would get 4. It's minus 4 plus or minus 4 times the radical of 1 minus 17. That would be minus 16, right?
4i, 69.
So that's 16i divided by 8. So we have minus 1/2 plus or minus 2i. And so for this one, the solution would look like well,
X to the negative half. Cosine 2 natural log x.
that's your solution. And if I give you initial conditions, you solve for C1 and C2 the same way, plug in your initial conditions, use the system of equations to solve for them. If it's a non-homogeneous case, which I probably won't ask you a non-homogeneous case for this, you can pretend, write the form of the solution and plug it in here and solve for the coefficients. If the right side does not look like a polynomial, or a polynomial times a sine, or a polynomial times a cosine, or a polynomial times an exponential, you use variation parameters. Yeah, so that's Euler equation. So I'll definitely ask you about these. One other thing I want to mention. I don't know if one of these is exactly the same example, but you might recall, I don't know if you recall, on the first test, there was a point where I gave you an equation. And I say, here's a solution. Use the direction word to find another solution. Look back at that example, you'll notice that I gave you an Euler equation. You'll also notice that if you had done this, you would have found both solutions. So what I did was an Euler equation, I found these two solutions, and then I pretty much on the exam told you one of them, and had you derive the other one using reduction of order. And for the other version, I told them the other one, I had them derive the other one for using reduction of order. But if you look back at it, it was actually an Euler equation. You could have solved it directly using this method. But we didn't know that method at the time, so reduction of order is what we had.
So is this something like, is this a thing that we're gonna get tested on, or is it?
Oh yeah, for sure. Euler, it's a very important thing. I'm going to test you on this directly.
Okay, cool. I thought we were just gonna kind of use it as a stepping stone for something else.
We're also using it as a stepping stone for something else, but it is something that in its own right, you should know how to solve it.
I got to take a quick.
Yes.
Like the characteristic equations, are we gonna learn how to use Euler differentials for particular solutions and function.
I'm not gonna answer that. Like, if I say, well, I don't know whether I'm gonna give you a homogeneous one.
What's the Cauchy
Wow,
part?
that was such a
Huh?
good
The
question.
Cauchy part?
What?
The Cauchy part?
The Cauchy part? Or
Yeah, what about this Cauchy?
People usually don't plot that unless they're doing something higher than second order.
Oh,
Right? So then they're like, it's a Cauchy Euler equation. Like, you know, that's when you have to get serious. You have to invoke the spirit of Cauchy. But other than that, second order, yeah, it's a little Euler equation. They're not that bad. They just have their own kind of characteristic equation, which is called the initial equation. And you solve it based on what I told you before. Now, let's go back to the question about, or the problem about singular points. Suppose we have we wish to find a solution, say a power series solution. Near x naught, a singular point. Now, if the thing has no singular points, what we did before with power series solution is going to work. Just assume y looks like a n x minus x naught to the n series of that. You might go from negative to infinity if that's your thing. However, if I say, okay, I want a power series solution centered at 0, and you realize that if you plug in 0, this coefficient is 0, that's a problem. Then you just doing that series solution isn't going to work. So here's what we're going to do.
You take limits?
We're going to take limits, but more than that, we're going to kind of want this guy to fit into some framework that we already know how to solve. Namely, Euler's equations framework. Because it actually works out very nicely with that. So here's how we're going to actually get this to work. We are going to first put it in standard form. Now what I'm going to do is I'm going to multiply both sides by x squared. Now this is like x squared y double prime plus x squared q over p plus x squared r over p y equals 0. And here's how I'm going to kind of finagle things. I'm going to think of this as x squared y double prime plus I am going to move this x in. Think of it like this, x times q over p plus, think of this thing as x squared r over p equals 0.
Not the prime.
So now you see it looks like alpha x squared, which is 1, beta x. That's not a constant though, so that's going to be somewhat of an issue. And then just something, this thing is going to function like my gamma, right? So that's the kind of idea we're going with.
The y on top is supposed to be prime, right? To the x squared, a little bit p. Well, just. Alright.
And we can do this because we're assuming that our p of x is not actually going to be at the singular point. Because we divided everything by p.
Oh, here's why we do it. Now, we say hello to our old friend. Dumb luck now. Guessing. Well, we've kind of made it this far. I mean, come on. We've made it really far. Let's pretend the solution looks like this. Oh, what? That worked out? Awesome. Right? So I think at the end of the day, that's the message that differential equations have for us. You know, it's not about dumb luck, because the theory really fits it, and so it's about hope. It's about hope. You know that if you get one message from this class, that's the message I want you guys to get. Don't worry about a thing. Every little thing is going to be all right. That's differential equations. You're just like, I pray that a solution like this exists that behaves in exactly the way I want. Holy crap, that worked! It's going to work out. Okay, so I am basically going to say, as I'm approaching the singular point, this guy, his power series is going to behave like a constant. If I were to write it out as a power series, A0, A1x, blah, 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 all the terms with x's attached to them are kind of going to vanish away. And I'm going to be left with the constant term. Same thing here. So we are going to hope that as x approaches x naught, xq over p and x squared r over p behave like constants. In their power series. That's the assumption. That's the hope. I hope that I can treat this like an Euler equation, because why not? I know how to solve those guys very well. And by the way, if your x naught is something other than 0, you can kind of shift it by like an x minus x naught. Just multiply by x minus x naught squared, x minus x naught, etc. Right, so the equation that I'm about to write down are going to make sense. That is, we're hoping that if I take the limit as x approaches x naught of this kind of expression, x minus x naught times q over p, and the limit as x approaches x naught of x minus x naught squared of r over p approach finite numbers. Now, does this always exactly give me what I want? The answer is no. Sometimes this just doesn't work out. But don't worry, everything is going to be all right. Don't remember that. Right? When this works out, though, when this works, we call x naught a regular singular point. Right? Because you can solve that like a regular.
Irrational numbers finite?
Yeah, any finite number. It'll look like a quadratic. Right? As long as the limit exists and it's finite, we can actually pretend this is somewhat of a pseudo-Euler equation. Now, because it's not exactly an Euler equation, and we have a notation for this. Put that in. Your textbook and many other places would call this little p naught, and this guy they call little q naught. And so we have the following. The original equation will behave similarly being the key word. It's not exactly an Euler equation, but it will behave similarly to an Euler equation. With an initial equation that looks like r times r minus 1 plus p naught r plus q naught equals 0. Now that expression is going to be important. We're going to be able to find that somewhere later on in our series process. Now because it's not exactly an Euler equation, we know it's not going to look exactly like x to the r. That's too optimistic.
So just ask you to be closer to.
Moreover, we assume the solution, because it's similar, right? So it's not exactly x to the r. Looks like x to the r times a power series, right? So it's kind of like I'm doing reduction of order. Pretend the solution looks like a solution I already have times some other function, but this time the function is going to be a power series, a n x minus x naught to the n. So in other words, we get something that was x minus x naught. We're thinking of shifting to x naught, and so we end up with a series that looks like this: a x minus x naught to the n plus r. And that kind of makes sense. Finding a series solution in the regular old way just doesn't seem to work here because we have division by 0. However, if we shift it just a little bit, you know, x squared is giving us a problem. What about x to the 2.1? Just a little, just a little bit. And it turns out this actually works out. It works out at the end. Right? You can go through the theory, you can find a power series solution that has this form.
Is the power series convergent?
We have to actually work it out. So we don't know ahead of time. If something like this works out, this is going to be a very nice way to get to the answer. But it might not work out. One, that might not be finite. In that case, we say we have an irregular singular point, which we're not going to do here. There's a whole other method to deal with those guys. But for regular singular points, whenever these two limits work out, a series like this can solve it. So you just need to find the coefficients. So, to solve an ODE, by series near a regular singular point, we assume our y looks like that. N goes from 0 to infinity. You're allowed to do the minus infinity to infinity version. X minus x naught to the n plus r. And that leads us into the next section, which we'll start next time. So we're going to look at linear ODEs, where we have a singular point. We want to solve it with a series because it's not quite an Euler equation. It's going to be almost an Euler equation. And we are going to use these kind of series to solve them. Which you'd be surprised. Guys that look like almost Euler equations show up all the time. They even have names. We have like Chebyshev's equation, Tessel's equation, Legendre's equation. There are a lot of guys that have this, like a y double prime with an x squared attached to it and pops up in applications. It's a very common thing to have. Which is also why we kind of look at this in the context of Euler's equation. Because just by going through applications, like this thing pops up, it's like there's a quadratic weaved into the second order linear ODE. So, hey, let's deal with that general case. That's an Euler equation. And then let's pretend that if we're kind of a little bit off of that, we can just shift our power series and it'll work out. And it does. So next time we'll actually do that. Also next time. So by next time you guys are going to be so used to doing this with series, you can fly through some series examples for this case. And hopefully we can start to talk about, I think, Laplace transforms next time. That's going to be fun. Yes.
Say if we don't get an extra
Then you say it's irregular. And then you can say we can't solve it. Like I wouldn't ask you to solve it. This is the only case we're going to deal with. The irregular case, we don't do it in this class.
How many places you found? Because after Thanksgiving, there's like, okay.
Yes, one more. Okay.
There's no quiz.